Hello, my name is Brian Crafton, and today I'll be presenting our work, Breaking Barriers, Maximizing Array Utilization for Compute and Memory, which is a conference paper at VLSI-SoC 2020. My co-authors are Samuel Spedalnik, Gutharam Murali, Tushar Krishna, Sungkyu Lim, and Arijit Chowdhury, and we're all from the School of Electrical and Computer Engineering at Georgia Institute of Technology. To start, I'm going to be going over some background information that's essential to understanding our research contribution. There's quite a bit to cover, but once we make it through and I present some data, the new technique becomes intuitive, and I bet some of you will figure it out before I even go through the details. In this work, we use a 128 by 128 crossbar array memory, which could be either PCRAM, RRAM, or any other non-volatile memory. We assume binary weighted cells and 8-bit weights and 8 inputs. For 8-bit weights, we use 8 adjacent cells. This means that our 128 by 128 array can store a 128 by 16 8-bit matrix. We choose 3-bit ADCs because the state-of-the-art devices achieve 5% variance, making 8 rows, and hence a 3-bit ADC, a reasonable choice for 4 or 5 sigma error. We assume 8 adjacent columns share an ADC, so there is only one comparator per column. At the bottom of each array, we have shift and add units to implement the rest of our matrix multiplication. In the following slides, we will see how this configuration allows us to perform a standalone 128 by 16 partial matrix multiplication in 1024 cycles. In the following examples, I'll be using 3 elements to go over the operation of a 128 by 128 array. The first of these is shown here on the right. It is a 128 by 128 array divided into a 16 by 16 grid of 8 by 8 subarrays. We have 16 ADCs in the bottom since every set of 8 columns shares an ADC. We choose to look at an 8 by 8 slice since these 8 rows will be read at the same time and the 8 adjacent columns will share an ADC. The last element is the input data, shown here on the far left. The data shown here is 8 of the 128 elements from the vector to be multiplied with our matrix. Since we are implementing an 8-bit neural network, there will be 8 binary values. The operation of this array can be thought of as 3 for loops. We first loop through the 16 rows of the array, since the results will be added together. Then we will loop through the 8 input bits, and lastly we loop through the 8 weight bits. To start, we begin with input bit 1, weight bit 1, and row 1, all highlighted below. Next, we proceed through all the rows. After completing all the rows, we proceed to input bit 2. And again, proceeding through all the rows. Finally, after going through all the input bits, we make it to input bit 8. And then again, going through all the rows, we ended up at weight bit 2. And this procedure continues until we make it to weight bit 8. And then we complete a 128 by 16 matrix multiplication. The cumulative number of cycles required for the whole operation is 1024 cycles because there's 8 weight bits, 8 input bits, and 16 rows. Now that we understand how these arrays can serve as both storage and compute for partial matrix multiplication, we can go through some mapping examples. For the first example, we want to map a 256 by 128 matrix multiplication to some hardware. Our hardware consists of 16 128 by 128 arrays. So if we slice up the 256 by 128 matrix into 16 128 by 16 matrices, it becomes clear that we can just map each one to one of our 16 PEs. So the figure on the right shows a color-coded version of how we do this mapping. In example 2, we go over the mapping for a convolutional layer. So we take a standard 3 by 3 by 64 by 64 convolutional layer and decompose it into a 576 by 64 matrix, similar to how it's implemented on machines today. So if we use the same strategies before, we can slice up our matrix into a 5 by 4 grid of these partial matrices. Note that the last slice is only 64 by 16 because 576 does not divide into 128. And again, the figure on the right shows a color-coded version of how we can do this mapping. Next, in example 3, we'll go over a larger example. We'll be mapping a 4-layer CNN to 512 128 by 128 arrays. In the table on the right, we show the shape of each layer in our CNN and the total number of arrays required to store it. But we note that none of these layers requires 512 arrays. In fact, they require significantly less. So what do we do with the leftover arrays? Prior work duplicates these arrays and performs a distributed workload, either parallelizing over the feature maps in the CNN or over different batches in a different model. In a naive implementation, we would reprogram the arrays after each layer to the new layer. And in the table below, we append the previous table with the number of duplicates we can have for each layer. And so for the first layer, we can duplicate 128 times, since 512 divided by the 4 arrays equals 128 duplicates. But using this strategy, you run into an issue. Writing to embedded non-volatile memories like PC RAM or RRAM requires significantly higher write power and higher write time than traditional memories like SRAM or DRAM. Therefore, we cannot rewrite the weights. So what can we do? Our solution becomes layer pipelining, where we evenly distribute the arrays amongst the layers. Then we pipeline the layers in our hardware. For illustration, we reference the figure on the right-hand side where, in each time slice, each hardware unit is processing a certain layer, but data from a different input batch. This allows us to achieve ideal throughput at the cost of higher latency. So now we can try to perform allocation for our CNN. In the figure on the bottom left, we map a single copy of our CNN to the 512 array hardware. Noting that we have many arrays left over, we can compute the maximum number of duplicates we can have by dividing 512 by the total number of arrays required to store a single copy. In this case, the floor of that number is 3, so we can copy our CNN 3 times. But again, we run into another issue. Since we are pipelining the layers, it's essential they all take nearly the same amount of time, because our faster layers must stall for the slower layers, and thus our performance is limited to the slowest layer. We find that even though we evenly distribute our arrays amongst the layers, we have not evenly distributed the workload. So if we list out the other parameters of the layers and then compute the total number of cycles required for each layer, as in the table below, we find that layer 4 takes a quarter of the time of the other layers while using more than half the arrays in our hardware, and hence we must allocate arrays based on workload, not evenly copying each layer. Okay, so we have made it through the background section of our presentation. Next, we will quickly go through the zero-skipping readout technique. And while this is not a novel contribution of ours, our handling of its impact on performance is. There are 2 simple ways to read the rows of an array: the baseline technique and zero-skipping technique. In this example, we will show an 8-row subset of a design with 2-bit ADCs. The input values are shown on the left-hand side, and we will just look at the first input bit to explain these techniques. Starting with the baseline technique, we can read 4 rows at a time since we have 2-bit ADCs, and we do not want to potentially overflow our ADCs by reading more than 4 rows. Therefore, the 8-row subset takes 2 cycles. However, if one is clever, they can use zero-skipping to perform this in a single cycle. The important thing to note is that there are only 4 ones in this subset of 8 rows, and thus we will not overflow our ADC if we just read the 4 rows containing 1s. So in review, current work assumes deterministic compute time per array discussed earlier in this presentation. This ignores zero-skipping or processes a whole column at once, ignoring variance and the number of rows in the column to create a deterministic compute time. Using zero-skipping creates a non-deterministic compute time at each array, which is dependent on the input data. And so if we assume 8 cycles per input, 8 cycles per wait, and 1 to 16 cycles for the 128 rows, then zero-skipping can perform the 128 by 16 matrix multiplication in 64 to 124 cycles. And therefore, there is no reason not to use zero-skipping, since it only improves the performance of each array. Now we have made it through all the required background information and can discuss our research contribution. Earlier in our presentation, we discussed how to allocate arrays based on workload, or total max, in the design. We want each layer to take the same amount of time, and assuming that each array took the same amount of time, this method was valid. However, zero-skipping complicates this. If the distribution of ones in the input data is skewed between layers, then each layer's arrays will have a different performance. And so our new, more complete equation is the total number of max in the layer divided by the number of arrays times the performance of each array. But how can we measure this parameter, array performance? A very simple proxy for array performance is just profiling the number of ones in the input data. And so over some samples, we collect percentages that reflect the rest of the data to come. On the right-hand side, I provide two examples for how we do this. Of the three input values shown in the two vectors, input vector 1 has 5 ones, and input vector 2 has 19 ones. Thus, we can expect input vector 2 to take longer. Now, this sample is fine, but how about some real data? So in the figure on the bottom right, we plot the cycles per 128 by 128 array versus the percentage of ones in ResNet 18. Each point in this plot corresponds to the average number of cycles of each array in the given layer over several samples in ResNet 18. So the variation between layers is massive. Some taking 70 cycles, others taking 100, 200, and even 500 cycles. And so this skew greatly changes how we wish to allocate our arrays per layer. By just plugging in this performance measurement, we can greatly improve array utilization and thus performance. We will see results for this later on, but first we ask ourselves, can we go further? And the answer is yes. Each matrix is made up of a distributed group of arrays. For example, on the left-hand side, we show a slightly larger version of our previous example. This convolutional filter is 3 by 3 by 128 by 128. We use a 9 by 8 grid of 128 by 128 arrays to create this matrix. The important thing to note is that all arrays in the same row of the grid share the same inputs and word lines. We call each independent row a block. So given that different blocks perform independently, we can allocate based on block instead of layer. And so if the blocks contain different input value distributions, we'll allocate a different number of duplicates to each block. Again, looking at ResNet 18, we focus on two layers, layer 10 and layer 15. In the figure on the right, we plot the cycle per block and percentage of ones in the given block. For layer 10, we see a 12% difference in cycle time between fastest block and slowest block. And for layer 15, we see a 27% difference in cycle time between the fastest block and the slowest block. And while these differences are not as large as the layer to layer, we can still exploit this for performance. So now using these new allocation policies, we will go over our results and the simulations used to collect them. For our simulations, we try several designs, sweeping the number of PEs in each design. These PEs are connected through an N-by-N mesh. Each PE contains 64 of the arrays we have discussed with virtualized I/O, so that way we can have different layers in the same PE. We have several CMOS memories on chip, namely DRAM, global buffer, partial sum buffer, and a result buffer. The CMOS-based vector units implement addition, quantization, and ReLU operations, and they also collect partial sums generated by the blocks and add these together. Our simulator is implemented in Python but uses C++ for array-level operations. Components such as ADCs and arrays are modeled in an object-oriented fashion, and each cycle we iterate through all components performing whatever operation should occur on that cycle. As input, we provide the CNN weights and input images, as well as a description of the hardware including ADC specs, array size, and the number of PEs. We also specify the array allocation policy. As output, the simulator generates performance counters and the actual result of each layer, which we verify against a TensorFlow implementation for correctness. For our simulations, we assume a 100 megahertz clock and sweep 5 different designs containing different numbers of PEs. First, we show VGG 11 on CIFAR 10 using the various methods we have discussed throughout this presentation. For reference, I have provided this table so the viewer can refer back to the previous point in the video if necessary. We observe a 7x improvement over prior work in the baseline and weight-based allocation methods. By allocating based on block instead of layers, using performance-based methods, we can obtain a 19% speedup. Looking at ResNet 18 on ImageNet, we realize even larger speedups, given that the pipeline is deeper and becomes more difficult to balance properly. We observe an 8.83x performance improvement over the prior work in this case. To better illustrate where this performance advantage comes from, we show the utilization of each layer in ResNet 18. Again, we show the table for reference so the viewer can refer to previous points in the video. Utilization is measured as active cycles divided by total cycles, so this essentially measures the time spent stalling while other blocks or layers finished. So in this figure, blockwise allocation dominates the other methods for nearly every layer. It is interesting to note how poorly allocated the weight-based method works for a deep network like this. So in summary, array utilization is a fundamental limitation to performance. Zero skipping causes non-deterministic compute time that previous work does not consider. And performance-based blockwise allocation yields the best performance, showing a 7.8x improvement over prior work.